Good morning. Groups 2, 3, and 4 for nanomaterials. Well, according with the syllabus, we have this week the hardness test. This is postponed for the time when we have availability for the lab. So we pass to the time topic number 9, solid solutions, phase diagrams, partial solubility, and TTT diagrams. Until this topic, the exam. Well, the exam for any group in 31st March and 1st April. Well, how we will develop the exam as a report. So I deliver you the template, you fulfill the case, you apply your criteria, and you emit your opinions. And I check individually why you answer it. Well, for this session, as we have available Teams as a platform, CTA is doing the change for Virtual Savannah to Teams. So please open this group, nanomaterials, group number 2, for example. I have also group number 3 and number 4. And for each group, you select the code. I send to your emails the code for each group, and here as a message I post the videos for each class. You answer me with the question and activity, and I create a WhatsApp group for receive your questions. In the case that we have to develop seminars, possibly we use YouTube, and you upload the video here as an answer. Well, the topic for today, the TTT diagrams. What means TT? Thermal or temperature time transformation. It's an isothermal transformation, and we have talked about annealing and tempering, the two main thermal processes. Annealing for make a metal soft, for relax a ceramic and distress polymers, and tempering for increase the hardness in metals, and also increase the toughness in glasses and ceramic glasses. Each thermal process has a beginning, starting from heat the sample close to the 80% of the melting point. This is an example for a common steel. So we raise the temperature until 1000 Celsius. Initially, both processes has the same starting, more or less 30 minutes, in order to achieve the internal temperature equal to the external. What differentiates is the cooling. If the cooling is faster, we are doing a quenching. If the cooling is slowly, we have an annealing. Remember that in these thermal processes, following by metallography, the size grain or the grain size increase by diffusion, but also there are another procedures. For example, the reorganization of the matter. In metals, we have the phase close to the melting point, and this phase transform in another crystalline phases. Never change the composition, change the crystalline phase. And that's the situation that we analyze today. In a common thermal process, we can use different heating and cooling rates. As we vary the cooling rate, the recrystallization, we will see the solidification process after this week, after the exercises next week. Today only the recrystallization. If you change the time of cooling, the size of the grain change. By metallography, it's possible to confirm that we have this modification. The grain increase in size by the diffusion. And remember the concept of dislocation climbing. If the grain has a bigger size, the climbing or creep can occur in more abundance, so the material can absorb the energy and don't break faster than other materials. In this example, if you cool in 1, 10, 100 or 1000 hours, the size of the grain also increase. Faster the time, bigger the grain, and shorter the time, smaller the grain. The grain matters. Remember that the creep cannot pass the boundary. If the creep cannot pass the boundary, it's stopped and the material accumulates stresses. So we can increase the hardness, but the fragility too. Well, I focus in steel, in common carbon steel. Common carbon steel, the main phase close to the melting point is the austenite or austenite. It doesn't matter what you want to spell. Austenite is 0.4 carbon in steel and has no, well, it's the most common structure, the most simpler structure. Anytime you cool the austenite, you can pass to another phases. For example, by diffusion you obtain carbides, and these carbides can create perlite, ferrite, or the mixture of perlite and ferrite, cementite or cementite. What differentiates the austenite from ferrite, perlite, and cementite? The hardness, the distribution of carbides, and the toughness. As we have said previously, the grain size. If you cool very faster, it's commonly to obtain martensite. Martensite is the most common in structure when you quench the steel. In other metals, for example, bronzes, aluminum, brasses, we need to label the phases with Greek numbers or Greek letters, sorry. For example, alpha, beta, gamma, etc. But in steel, they have specialized names: austenite, martensite, ferrite, perlite, and cementite, and also the bainite and nanobainite, and spheroidite. But in the next slide, I will explain. Any thermal process starts with the slope of heating. Then you heat until the melting point. For example, if you have aluminum, you can heat until 500, 600 Celsius. Then you retain the temperature or hot by 30 minutes, and then you can cool in several stages. Why in several stages? To pass from one crystalline phase to another phase. Usually you can quench using air, dry air, in order to avoid the rusting or corrosion, or using a thermal oil. Never in water. In Fab Lab, we can do the experiment with water, but it's preferable to use thermal oils, for example, the cooling oils, the common car cooling oils. In the thermal process, we can observe formation of a crust. It's a carbide that diffuses to the surface and is separated after cooling. This is an example of the hardness measured in the Becker scale after different time of cooling. So if you increase the time of cooling, this material, this is a mixture of copper, zinc, brass, the hardness decreases. So remember, if the time of cooling increase, the grain size increase, the creep increase also in amount, in abundance, and finally the hardness of the material decrease. This happens exclusively in metals. In some stainless steels, could happen that the hardness decrease even in tempering. In some plastics, if you temper, what occurs is you don't let the molecule to recover the initial size. It's a spring, so it's stressed. The objective of annealing is this stress the material. Here is an example of tempering. So in tempering, this line, this vertical line, the quenching, don't let pass the austenite to intermediate phases, for example, ferrite and perlite. Pass directly to martensite. And the martensite has a small grain, it's so hard, is the phase preferred to create hard steels. In tempering, we have two sections, the austenizing and the austempering. In steel, austenize is to heat the sample close to melting point, more or less 900 Celsius. And austempering is to retain or hold the cooling around 350 and 40 Celsius degrees. What's the goal of austempering? Let diffuse the grain and let to create the secondary phases. Then that you have exhausted all the austenite, you can cool using air, and you can extract the sample at 80 or 60 Celsius degrees. So remember the difference. In annealing, you have a slow rate of cooling in several stages. Slow means more than 10 seconds. In more than 10 seconds, preferably more than 10 minutes, and very preferably more than hours. If you anneal the sample in hours, you ensure diffusion and the grain grows more. You obtain a big grain. In the quenching, you apply a coolant substance, gas, oil, or others, and you crystallize and solidify the material very fast, and you obtain a more detailed phase. For example, in steel, austenite pass to martensite. But if you anneal the material, the austenite pass to intermediate phases. For example, ferrite, perlite, bainite, and others, and they are soft. How to understand what kind of phases you will obtain? Well, we need to study the phase diagram. The phase diagram, for example, in binary materials, contains the percentage of a material solubilized into another. Remember always the solubility limits. For example, carbon is hexagonal and iron is cubic, so the solubility is slow. If you trespass the limits of solubility, you have segregation, not a dissolution. In the case of steel, 1% is the limit, and less than 0.4 is better. The austenite is a solid structure, and once that you have cooled the sample, you pass and reorganize the material in another structures. For example, in steel, austenite reorganized in perlite. In this line, in 0.4, touching this minimum, the eutectode point. Touching the eutectode point, you make a cut, and you can follow the cooling process. The cooling process, for example, like this line, you start in austenite, and this diagram has new lines. These are the phases lines. Once that you have touched a phase line, you pass from one crystalline structure to another crystalline structure. And in TTT diagrams, we have several phase lines. So it's possible to pass from one crystalline phase to another crystalline phase. They are not reversible. It's not possible to pass, for example, from bainite to austenite again. The austenite in steel is the raw matter that can convert into another's. So if one given percentage of austenite pass to bainite or pass to perlite, disappear immediately. It's not reversible. So only the percentage that doesn't pass to the next phase is available to convert into another. In this exercise, for example, a portion of austenite passed to bainite, and the remaining percentage, if it's cooled or quenched, passed to martensite. So we have a mixture. It's crystalline phase martensite and crystalline phase bainite. Have you questions at this point? Please make me your questions. And I continue in another video with another cases in ceramics classes and exercises for the next session.